Okay, thanks, Sujit. So, good morning, everyone. My name is Yujen Ku, and as Sujit mentioned, okay. As Sujit mentioned, I'm the PhD student of Sujit, and today I'm going to introduce one of our studies, the sustainable vehicular edge computing using local and solar power roadside unit resources. So nowadays, vehicle applications ranging from ADAS to self-driving applications are relying more and more on computations. But not every vehicle has that much computing capacity to provide such compute-intensive vehicle applications. In that case, roadside units can be a solution. Roadside units can create overlapping small cells along the road and provide high bandwidth and computing capacity to vehicles, allowing them to offload their computation tasks. However, with the dense deployed roadside unit, the total energy consumption will be a huge issue. Therefore, in this study, we're focusing on the use of solar-powered roadside unit, or we call it SRSU. SRSU consists of a small cell, and a vehicular edge computing node. We call it VEC, and a VEC manager, and also the solar panels. So the SRSU not only ease the burden of total energy consumption, but also make the deployment of the roadside unit much easier for on-demand and rural areas. So in some sense, in my opinion, I think SRSU also provides solutions for one of the goals that Ted mentioned earlier, to improve the connectivity of the rural areas. Furthermore, in this study, we're also focusing on the management of the distributed two-tier computing resources. That is the VEC node inside the SRSU, and also the vehicle users or VU's local computing node, VLC. Our main problem is to study how to allocate the computing resources of VEC inside SRSU and VLC to each VU's computation task, such that the task disruption is minimized. This problem will involve three challenges. First is that SRSU might run out of power because the solar energy is limited and fluctuating. And second, vehicles is moving very fast, which will induce fast-changing communication and computing demand for each SRSU. And the third is the dynamic availability of both computing and the bandwidth resources. So to solve this problem and address the above challenges, our approach will involve the VU-SRSU association, task partition, and the SRSU communication and computing resource allocations to be used at in each time slot. So in this study, we focusing on the VU task as the following. So we assume the task of VU consists of a sequence of subtasks, and each of which can be offloaded or executed locally. So to ensure the service quality, the overall delay of the task should be less than DIT for VUI at time slot T. So DIT will include the following. First is the execution delay of the subtask that are executed locally. And if VU choose to offload any subtasks to the SRSU, then there is an uplink transmission delay to upload those offloaded subtasks, and the execution delay by using the VEC, and finally the downlink transmission delay to download the results back to the VU. And finally is the local execution delay of the rest of the subtasks. So for those VUs which do not have enough VLC capacity, the SRSU has to allocate enough VEC computing and bandwidth resources to VU so that the delay constraint can be satisfied. So this slide shows the overview of the SRSU assisted vehicular edge computing ecosystem. At the beginning of each time slot, the VU will inform SRSU its VLC capacity, the delay constraints, and its task compositions. And the VEC manager inside each SRSU will collect this information along with the channel conditions and the SRSU's energy, VEC, and bandwidth availabilities. And different SRSU's VEC manager will collab together and jointly make the VU-SRSU association, resource allocation, and task partitioning decisions, which will be sent back to SRSU and each VU. So based on the decision, each VU will offload the corresponding subtasks to the SRSU. So in this problem, we consider to minimize three kinds of cases that will impact the service quality of a VU: service outage, service disruption, and the local computing ratio. So the first service outage happens when the VU's task delay cannot be satisfied by VEC or VLC. So we use the term LDT here to represent the number of VUs that's experiencing service outage at time start t. And the second is the service disruption, which happens when the VU is being handed over to another SRSU. Because during the handover process, it will create a small break that the VU cannot receive any offloading service from an SRSU. We use LHT here to represent the total number of users that are having service disruption at time start t. So the third is the local computing ratio, which is the portion of VU's tasks that are executed locally. Since there might be other applications sharing the VLC capacity resources, so our target vehicular task might experience higher than expected delay. So therefore we want to minimize the portion of the VU's tasks that are executed locally. We use LLT here to represent this portion. So our overall objective is defined as follows, or we call it the QS loss, where here the kappa and sigma are the weighting factors for the second and the third cases. Our problem can therefore be formulated as to determine the association of offloading set, which is the set of subtasks that the VU will offload to SRSU, and the SRSU's resource allocations at each time start to minimize the QS loss under task delay requirements, the VLC's capacity, and SRSU's solar energy, computing resource, and the communication resource availabilities. We name it this problem P1, which is this. List here, and notice that the parameters and the solutions of P1 will be different across different time slots. Here, P1 also have some other constraints, such as a VU can only be associated with one SRSU, and also that SRSU needs to provide a certain signal strength. So we observe that P1 is a nonlinear integer programming problem and is NP hard. Therefore, we will solve P1 by its dual problem. We will rewrite the objective function, and then we will dualize the resource constraints of P1 and form the dual problem P1LD by using Lagrangian relaxation. Here we call the new objective function here as the dual cost. And notice that the dual cost including not only our decision variables, but also the Lagrangian multipliers here. So to reduce the time complexity of our algorithm, we decide to update the value of Lagrangian multipliers by the resource utilization rate of previous time slots. So that is, the more resource you utilize in the previous time slots, the more dual cost you will get at current time slots. On the other hand, we will allocate the communication and computing resource of SRSU proportional to its resource availability at time start t, while satisfying the VU's task, the delay constraint DIT. So with these two decisions, P1LD will be equivalent to finding the SRSU and offloading set, which minimize the dual cost for each VUI. In that case, our algorithm will first pick the VUI that has the minimum regret in terms of the dual cost, and we'll make the SRSU association and offloading set decision for that VU, which corresponds to the minimal dual cost. And in the meantime, we'll check the resource availabilities. After we make the association decision, we'll update the dual cost for the rest of the VUs, and we'll repeat the above steps until all the VUs, until there is no VU can be associated. So in the following slides, we will evaluate our approach by a framework which simulates the real-world settings. We will use the historical data of a Brooklyn neighborhood, and this top figure shows that Brooklyn neighborhood and the placement of our 13 SRSUs. We assume the VU task consists of two subtasks, which is video encoding and then object detection. We simulate the VEC node as 5 NVIDIA Jetson TX2 modules, and for solar energy, we use the data collected at UC San Diego, and the simulation period is from 10 a.m. to 5 p.m. so that SRSU can collect solar energy. So this slide shows the service loss performance under different solar panel size of our algorithm compared to another 3 techniques. The blue line here shows the performance of our approach, and the purple line here shows the performance of the approach without using any VLC resources. So as you can see from the left figure, our approach can achieve less than 4% of service outage rate when the solar panel size is 1.6 meters squared, which is higher than 50% better than the approach without using the VLC resources. So the same performance can also be seen in the figure on the right-hand side. So you can also observe that the performance starts to saturate after the solar panel size surpasses 1.6 meters squared, which is a reasonable solar panel sizes, as we will show very soon in our testbed design in the following slides. So this another slide shows the service loss performance under different computing capacity conditions. As you can see from these two figures, our approach can significantly reduce the service loss compared to other techniques when the number of Jetson modules inside each VEC increases. Our approach can achieve as low as 4% service outage rate and 0.1 QoS loss with only 5 Jetson modules. So finally here, like Suji has mentioned previously in this session, we are building multiple testbeds for our STIP program. Here I will introduce one of our ongoing projects to build the renewable energy powered roadside unit prototype and testbed. So this testbed will include a 1.7 meter square solar panel and a wind turbine with 1.3 meter blades. In this testbed, we use ME Jetson TX2 board and the USRP B210 to emulate the small cell and the MVC server. We also have multiple sensors to measure in real time the power generation, consumption, and also some environmental factors such as temperature, battery voltage. The figures on the right-hand side shows the example of solar power generation, wind power generation, and battery voltage data that we collected for a whole day. So as for the future work, we aim to emulate the solar and wind power generation and roadside units power consumption under various real-world weather and offloading demand conditions. And we will validate and demonstrate our proposed approaches to enable the renewable energy powered roadside unit. Finally, we will develop a machine learning model which can predict the energy availability of a renewable energy powered roadside unit based on current energy generation, battery, and environment conditions, and the offloading demands. These prediction results will be used in developing an online adaptive battery scheduling algorithm which can improve the sustainability and longevity of the roadside unit operation. And I think that wraps up my presentation. Thank you very much.
Thank you, Yujen. One or two quick questions? Yes.
So what are your assumptions on the connectivity? Hi, this is Ted Woodward with Facebook. I'm just wondering, what were your assumptions on the connectivity of the roadside units between the units?
So here I just assume there's a backhaul. It can be wireless or it can be wired.
Okay, thank you.
Thank you.
Yes, that's a very good question. And in our test bed, we are implementing in one way, but there is a lot to be discussed there, right? That, but the way we are designing, that each SRSU will be bearing the brunt of the data traffic as well as the analytics and everything. So most computation, everything will happen locally, and only some data will trickle up. And yes, because of Eugen's design, there'll be some control data going back and forth.